Okay, so this is second part B of the midterm review. So for discrete math, I should say. So last time we talked about sort of our two different types of logic. We talked about propositional logic, and we talked about predicate logic. Cool. So we talked about the differences, sort of really what they are. This is a bit of a reminder. Propositional logic is like functions. Predicate logic, so predicates like functions. Propositional is like variables. So however you want to view them. We also talked about quantifiers, so existential and universal, and talked about sort of just roughly how you'd go about working with them. So this time, what I'd like to talk about is proofs. So, sort of the second third of the stuff we've talked about so far. So proofs was sort of a key thing. And one thing that I notice, I'm going to sort of just talk through like a few common issues that I see with proofs. One major issue is, well, fundamentally the issue is that people don't know what proofs are. So one thing that people think of proofs is that you can give examples. Well, proofs are not examples. So if we ask you to prove something and you say something like, let's try, I don't know, x equals 1 or something, right? Basically, anytime you start using numbers, you've gone wrong. That's not always the case, but usually when you start having like setting variables equal to numbers, you've gone wrong. So with proofs, you don't want to use numbers. You don't want to have like tables or try a couple examples, right? Proofs should be like solid no matter what numbers you give, right? So let's say that I wanted you to show that, for example, let's say I wanted you to show that an odd number times an odd number is an odd number. Okay, well, maybe you say, well, we can check 3 times 5. Great, that's 15, it's odd. We can check 7 times 3, 21, great, it's odd. We can check 9 times 5, 45, great, it's odd. We've given 3 examples. You could give me 100 examples, but you still haven't done every possible example, right? What if there's some pair of odd numbers that you multiply and you get an even number, right? You haven't shown me that every possible pair is going to be odd. How do we do that? Well, we need to use formulas, right? And this is the hard part that people get with proofs. So with proofs, you want to be as clear as you can, right? It's important to be like organized. It's important to be very diligent. Okay, so maybe I'll just stop talking about that for now. So proofs are not examples. Number 2, don't use proposition logic or predicate logic. This is different. I mean, the concepts still apply, right? Of course, we talked about logic, we talked about how logic works. That's why we gave you that background, so that now you can use that background in proofs. But don't start your proof by saying something like P represents this, or P of X represents this. That doesn't constitute, well, it could be a proof, but if you start doing this, you're gonna really get lost. So what I would suggest is you avoid a lot of this. This is where people start to get hung up and caught up with a lot of this. So avoid the predicates, avoid the propositions, probably for the most part, avoid quantifiers, sorry. Maybe just vaguely in your writing, you can do something like, we want to show for all x that, right, some, like you're just sort of embedding it. You can embed these things in, but don't like, it's not as hard and fast as it was when we were doing propositional and predicate logic. So really don't worry too much about trying to force those in. Yeah, so don't use propositional or predicate logic. Another common issue people have is that you should write out your premises and conclusion. Okay, well, what is that? What are premises and what is the conclusion? I see a lot of people, especially on the quizzes, are having trouble with this. So let's see. So for example, if we have that same one from before where it was like an odd number plus, times an odd number equals an odd number. Okay. So if it's like that, then so then what our premise would be, and really when you start your proof, the first thing that you should be writing on the page, you know, it says questions up here, whatever, the first thing you should be writing is like premise, and then conclusion, right? So what's the premise here? Well, the premise is that we have two odd numbers. So think about like, what are we given? Premise is like, what are we given? We're given two odd numbers. Conclusion is what we want to show. We want to show, maybe we'll give them names. We'll say M and N. You can always give things names, right? So we'll give them names M and N. The conclusion is that M plus N is also odd. So think about it, right? Premise is what we start with. We start with the fact that we have two odd numbers, and what we want to end with is that M plus N is odd. When you add them, multiply. When you multiply them together, it's odd. Sorry about that if that was a bit confusing. Yeah. Okay, maybe let's actually try this proof. I'm going to erase some of this. Let's try this proof. So the question in this case might say, or maybe we'll do something slightly different because we've been doing the odd and even. Maybe we'll say like, show that an odd number times an even number is even. Okay, let's do it. So, first thing I should write, premise. Remember, you literally get marks for writing this on a quiz or on a test. Premise. The premise is that M and N, we're doing odd and even. So we'll say M is, how do I want to do this? I'm going to change the name. I'm going to call this E for even. E is even, and O is odd. So I have two variables, E and O. Cool. Our conclusion is that E times O is even. Okay, that's what we start. That's the first thing you write on the page. Next, we start the actual proof. This is just like sort of background work that you put up there so that we know you have an idea of what you're trying to do. Now you actually do it. So all proofs should start with the word proof, like this. Proof, we want to show that E times O is even. Once you write the word proof, write down your premise. Write it as like an assumption or a supposition. So write, in this case I'll write, suppose E is even. I know you're writing this out a lot, but that's okay. O is odd. Okay? Suppose E is even and O is odd. I usually write even here. Want to show E times O is even. Okay? So literally we're copying the premise and conclusion a second time. We're just writing it again on the paper. Okay? Great. So you've got that. We've supposed E is even and O is odd. From there, how can we get to E times O is even? So usually the way that we do proofs like this is we, how am I going to show this? So we sort of have two ways of talking about things. We have like words and we have math. So what you're going to do, you're usually going to start your problem in words, which is what we have here, right? This is all words. There's no math here. You're going to take your words and translate them into math. So translate them into math. Then once they're in math, you're going to solve the problem using math and then translate it back into words. This is how every proof is going to go. You're going to start with words, you're going to translate it into math, you're going to solve the math, and then you're going to translate it back into words. So we've got the words. Let's do the first step. Let's translate it into math. Okay, well, what are the mathy words? That's usually a good spot to start here. What are the sort of mathy words we have here? Well, really the big words that like evoke like math, right, are even and odd, right? You can literally underline them if you want. Okay, even and odd. So think to yourself, what does it mean to be even and what does it mean to be odd? Well, if a number E is even, so we can write then E, we can write even, E being even by saying that it's 2 times something. Let's call that something X. So 2 times X. 4, now, why am I explaining this further? So we've just introduced this random letter X. We don't know anything about what it is. So when you're writing a proof, you want to explain, anytime you introduce a new variable, explain what that variable is in words. So here, we've introduced X for some, in this case, X has to be an integer, right? For some integer, X. Now, how do I know that this is true? Just a lot of practice, right? These are all little definitions that were sprinkled throughout the course. So you just gotta keep those in the back of your mind. So when you see the word even, you can translate that into this statement. Okay. So now we've got that. Let's worry about odd next. So maybe I'll put like a comma here and I'll write and O equals, so we have O for odd. What's an odd number? Well, it's 2. I can't use X, so I've already used X, right? We don't know that this X and this X are the same, right? So I'm going to use a new variable, let's call it Y. So 2 times Y plus 1. That's what it means for something to be odd. It's, you take a multiple of 2 and then you add 1 to it. Or subtract 1, either's fine. In this case, I'm just going to add 1. And again, I've thrown this random letter Y in here. We haven't introduced what Y is, so I have to explain. So for Y, I should write this for some integer Y. Cool. Now what do we want? Well, we want to show that E times O is even. That's why we write these up here at the very top, so that you can look back and say, oh, this is the end goal. I want to show that E times O is even. Okay, so what's E times O? Maybe I should just take a quick break here. So we finished translation. We're at this point now, right? We finished translation from from word story to math. Now we're in math. We need to solve the problem. So at this step here, I usually look back here and say, okay, what's the problem I want to solve? I want to solve that E times O is even. So now, let's figure out what E times O is with all this math, right? Okay, so E times O, well, what's E? E is 2x times O is 2y plus 1. Now let's multiply them. So 2x times 2y is 4xy plus 2x. Okay. So now, once we've sort of gotten to that point, we need to think about, maybe a good way to think about this is that we want to sort of plan out how we're going to come around this corner and start translating. The ending we want to show is that this is even. So we want to show that this number is even. Well, is it even? What does it mean to be even, right? A number is even if you can write it as 2 times some integer. Well, this is 2 times 2xy plus x. So it's 2 times some number. So we've shown that it's even, and maybe we can write that. So we'll say, so E times O is 2 times some integer, which is 2xy plus x. Therefore, and this is sort of the last phase here, we've kind of bent around that corner. We've finished solving, and now we're starting to work our way to translation, back to words. So therefore, E times O is even. Hopefully that makes sense, and I hope this sort of example gave you something. Okay, so we've done this proof that E times O is even. We need to end the proof. Always end the proof using a little box or the letters Q, E, D, whichever you prefer. It's sort of like the math version of a mic drop. It's boom, I showed you, we're done, right? So yeah, just like how in English, maybe you start your sentence with a capital and you end your sentence with a period. In math, writing proofs, start the proof with the word proof and end the proof with either a square or QED, whatever you prefer. One thing I want you to notice about this is that what I did not do is I did not just write a string of equations. Strings of equations can be a proof, but they're not what you're supposed to do. You're supposed to write a proof using words. So I did have some equations here, but my proof is not just a string of equations where I write down some equations. You want to use words, right? That's really often someplace that people struggle. So make sure that you're using words. Take your time, right? We give you time to write these proofs. So take your time. And I promise you that if you write premise and conclusion, literally just writing those out twice, so writing premise, conclusion, and then starting your proof, suppose the premise, and then want to show the conclusion. If you do that every single time, it is going to help you, okay? It's going to help you to have an idea of a very subconscious, deep idea in your head about how you're going to go about this. all that time that you're spending writing, in your head, you're kind of thinking through it, whether you think you are or not. You're really working through this problem in your head subconsciously so that you have an idea of how you're going to approach it. And just writing these here, like I'm sure all of you, you've written a number of proofs now. When you're sitting there writing a proof, sometimes you just blank, right? Writing these is going to help you to stop from blanking. That is why we get you to write these, okay? It's so important. That's why I'm stressing it. Write them down. Plus you get marks for it, right? So literally, you're gonna be spending time thinking anyways. You might as well spend time thinking, writing this down, which is gonna actually help you think, okay? Yeah, so hopefully that helps. That's the basics of proof. So now what we're gonna do is we're gonna talk about a couple different proof strategies. So, I'm gonna erase some of this. Let's see. Okay, so, proof strategies. All right, so some proof strategies are, there's usually a few that you typically are going to use. The first one is direct proof, which is what we just did. Maybe I'm going to use a different color here. I'm going to give you examples for each so that you can practice. Just to like get used to it. Let me think here. I want you to prove that, let's see, it's a difficult one. Well, let's just say prove that an odd number times an odd number, its result is always going to be an odd number. I know I talked about it, but I want you to try and work through it. Okay. Number two. Contraposition. What is contraposition? Well, contraposition is where you, so normally with a direct proof, you assume P and you try to show Q, right? That's a direct proof. And P and Q, they're just like, I don't know, maybe instead of using P and Q, I should probably use like, you start at the start, and you try to show the end. With contraposition, you start with the opposite of the end, and you try to show the opposite of the start. If you've done this, then you've actually showed this. So if you've shown that if you start at the opposite of the end and you get the opposite of the start, that is literally the same thing as showing if you start at the start, you get to the end. It's a convoluted way, but sometimes it's easier, right? Sometimes this is going to be the easier approach. Cool. Let's think of a good contraposition example. Let's see. Prove that there let's see. Well, we do something similar, right? We could say why don't we, I'm going to ask you to do a similar proof. I'm going to ask you to prove, oh, this is an awful marker. Sorry. I'm going to ask you, this is also an awful marker. Is this one going to be any better? That's better. Prove. I want you to prove that if you have two numbers, let's say both are odd, then their product is, well, let's say both are, yeah, I'll give this to you again. Both are odd, then their product is odd. And this almost sounds the same as this. I just put a few more words into it, but I want you to show this using contraposition. Okay, so show the same proof using contraposition. Okay, the third basic one is contradiction. So what's contradiction? You start at the opposite of the start. Now that's different from contraposition. Contraposition, you start at the opposite of the end. Here you start at the opposite of the start. And you want to show in contradiction that basically that, I don't know if this is a bad boom, but that math goes up in flames. Boom, lightning, bad. Okay, sad face. Okay, you want to start at the opposite of the start and show that things go wrong. What do I mean by things go wrong? Well, there's sort of two pieces here. One of them is either you start at the opposite of the start. If you start at the opposite of the start and you do math, sometimes you can show that the start is true. Well, if you start at the opposite of the start, let's say that like this start is like, I don't know, that you have an odd number. If you assume that you have an odd number, then you do a bunch of math, and at the end of the day, you have an even number, well, how's that possible? Number can't be odd and even, right? So you've sort of just broken things down. That's one way you can do it. Another way you can do it is that you start at the opposite of the start, and then math breaks. So what do I mean by math breaks? Well, what I mean is like maybe you do a bunch of work and you end up showing that 1 equals 2. Well, that's not true. 1 does not equal 2. So if you assume the opposite of the start and you show that 1 equals 2, this is false. So that means this has to be false, which means the start has to be true, right? So this is sort of the way that we go about this. So an example of this is, let's see, prove that there are infinitely many multiples of 3. Maybe a better way to write this is numbers that are, and I'm actually going to change it a little bit, numbers that are divisible by both 7 and 13. So give it a try. Show that there are infinitely many numbers that are divisible by both 7 and 13. So both of them at the same time. You can do that by contradiction. And why would I use contradiction here? Often, like this is just not always true, but often a hint that you want to use contradiction is that you see the word infinite somewhere in there. That's not always. There's some cases where you see infinite and it doesn't mean contradiction, and there's some cases where infinite is in the question and you're not supposed to use contradiction. But in this case, you are supposed to use contradiction. Did my laptop shut off? Hopefully I'm still recording. Yeah, looks like I'm still recording. Okay, sorry about that. Yeah, so in this case, you do want to use contradiction. And the reason contradiction is nice is because instead of working with infinitely many things, you can take the opposite of that, and now you're working with finitely many things. So what you'll do is you'll say, suppose that there are finitely many numbers that are divisible by both 7 and 13, and show that either math blows up or that there's not finitely many. Hopefully that makes sense. And try and keep yourself organized with all of these proofs. One more type of proof that's often used here, if I can find my black marker here. Maybe I'll write it down here as 4, is cases. Okay? So proof by cases. What is a proof by cases? Well, a proof by cases is where you take a problem. So say that you have like some problem here. This is your original problem. And you break it into multiple little cases. And then if you go around and you prove each of these 3 cases, then you've proved the original, right? The very, very important piece here is that you have to make sure that these 3 are all of the cases, that it encompasses everything, right? You don't want there to be like an extra case that you forgot about, because if you only did 3 of the 4, then you haven't done all of them. So you haven't solved everything, right? Yeah, so that's another strategy, and I'll let you go to the textbook for some examples of this. One more strategy I just want to give you is proofs of existence and uniqueness. Okay, so what do I mean by that? Well, if a question says something like, show that there's, actually here's a good example. It's a bit harder, but I'll write it in red. So an example for this one is show that there is only one number that, let's see here, only one number that you can how do I do this? There's only one number that you can, I'm gonna rewrite this. Show that there's only one number x, so that for any number y, x plus y equals y. So how do we do this? Well, for existence and uniqueness proofs, we want to say, okay, well, first off, you want to show that there is at least one. So just come up with an example. That's the existence part. You want to show that there's at least one example. If you can find one example, great. You've showed that at least one exists. So, you know, there is such a number x. The next part is that you want to show there's only one. So you've shown that there's at least one, then you have to show that there's only one. A good way to show that there's only one is by contradiction. So use contradiction. Assume that there's 2. So assume that there are actually 2 of them, and then show that they're actually the same is how you would do that for uniqueness. That's a uniqueness proof. You assume that there's 2, and then you end up showing that they're actually just the same thing with different names. So x, you know, if you call them like x1 and x2, then you end up showing that x1 equals x2. So they actually aren't different. So there is only one. Hopefully that makes sense. So I think that's the most of the proof strategies here. I know that was a bit of a longer one, but I hope it was helpful, and I hope you could sort of get an idea of how proofs work with this. Awesome. I'm going to stop the recording, and we'll do a part 3 on sort of sets, functions, sequences. I think that's all we did. So we're going to do another part on that, and then that'll be it.